Here's the last example, and it says use Newton's method to find all of the solutions to the equation correct at 8 decimal places. Alright, we're going to use Newton's method to help us do this. The only issue here is if you look at the previous problem, we always had an initial guess. Here, we're not given an initial guess, but we have to come up with one ourselves. So if you recall the pre-calc, here's where you could use some of that pre-calc knowledge. Something you should have learned is the rational root theorem, where this would be Q, this would be P. You could find all the P's over the factors of P over Q, and those would be the possible rational zeros to this function. Those could serve as initial guesses for Newton's method. That'd be a good way to do it. Not only that, in pre-calc you should have discussed the degrees of the polynomial versus the zeros. Since this is a 7th degree polynomial, we can conclude that we should have at most 7 zeros. We could have less, okay? Fortunately for us, this one has less than 7 zeros. We're not going to get 7 answers here. And I mean, there's a bunch of other techniques in pre-calc that you could have learned to help you figure out your initial guesses, okay? Switching over to calculus, what we're going to do is I'm going to pick the interval -1 to 1, okay? And by the intermediate value theorem, let's go ahead and find f of -1. F of -1 is equal to -7. F of 1 is equal to 7. So by the intermediate value theorem on this interval, it goes from negative to positive, meaning it has to cross 0 somewhere. This is a continuous function. It's a polynomial. Polynomials are continuous on the entire real line. So it's definitely continuous on any closed interval of the real line. So by the intermediate value theorem, we know there must exist at least one 0 on this interval. Now you could keep going ahead and trying different intervals, like you can do 1 to 2, let's see, 0 to 1, -1 to 1, and trying a whole bunch of things and see what intervals work, and you know there's zeros on those intervals. Pick a value from that interval as your starting value, okay? So let's go ahead and pick a number from here. I'm just going to randomly pick a number. Let's say our x1 is equal to 1/2. That's definitely on this interval. Now I'm going to apply Newton's method. So I have to enter this function into y1. After I entered into y1, I need to store x 1/2, store that into x. Same process as we have been doing. And then x minus y1 of x divided by dx of y1, x equals x, store that into x, or and derive, no e here, no e, y1 comma x, store that into x, depending on what calculator you have. Okay, now upon doing that, if I have 1/2 stored into x, let's see, I get an x2 of -0.93, hit enter again, x3 is -0.77, let's see, x4 is -0.7457. And then all I'm going to do is I'm going to keep hitting enter until it gets to an actual value where the digits don't change. As you can see, we're getting closer to some 0.7 number, negative 0.7 number. So let's see, I hit it a fifth time, 6, 7. After hitting it 7 times, we get negative 0.7446666792. The 6th iteration and the 7th iteration are exactly the same. That means we just found a 0 to this function right here. So let's go ahead and test it out. Let's take this number and plug it in. So f of negative 0.7446. I'm not going to plug in all of the digits. If you plug in all the digits, it might give you 0 or a very closer to 0 than this one. So let's see. Let me plug this in real quick. Negative 0.7446. You get 0.00138. That is really close to 0. Okay? Now, let's go ahead and let me check what it is when you put all of the digits. If you put all of the digits, it equals 3.305 times 10 to the negative 10. So that's 0.000003305. And actually, there's 1, 2, 3, 4, 5, 6. There's one more 0. That's really close to 0. So as you see, Newton's method worked really well to give us one of the zeros of the function. Whereas if we were in pre-calc without this, it'd be difficult to find this 0 right here. We would not be able to get it this accurate. We possibly could, but it would be a lot more work than what we just did here. Okay, so let me record our answer. X, root 1. I don't want to call it x1 because our x1s are our initial guesses. Root 1 is negative 0.7446. Alright, so now let's go ahead and try a different initial guess. Let's try negative 1/2. Now, it could bring us to the same 0, but our job is to find all of the solutions. So, if you recall, our interval was negative 1 to 1. The intermediate value theorem worked, but that says there's at least one 0. Okay, there could be more. We tried closer to 1, and it brought us here. Let's try closer to negative 1, and let's see if it brings us here. Or it possibly could bring us to another 0. We don't know unless we try. So, to do this on the calculator, to make it a little bit easier, store that value into your calculator. So negative 1/2, store into x. Now, if you hit second enter, I entered other things in my calculator, but if you keep hitting second enter, it'll eventually bring back up one of the options you did already, which was Newton's method on the calculator. Then you don't have to retype it. You could retype everything in. You don't have to. There's nothing wrong with retyping it. I'm just trying to show you a little bit faster way. Now, hit enter. x2 is equal to negative 0.89. Enter. x3 is equal to negative 0.76. Hit enter. Keep hitting enter. And it goes right back to this 0. Alright? So, I think we found the only 0 on that interval. So let's try a different interval. Let's try the interval from 1 to 2. We did negative 1 to 1. Let's try 1 to 2. If you recall, f of 1 was positive 7. And then if we plug in 2 here, we get negative 259. Well, look at that. Intermediate volume theorem states that there is a 0 somewhere on here because it goes from positive to negative. So let's test a value in this interval. I'm going to say my initial guess is 1.5. 1.5 is in this interval. And now just applying Newton's method, so I got to store 1.5. 1.5 store into x. I stored it into x, and then if I hit second enter, and then second enter one more time, it brought back up the derivative again, the Newton's method, and now just hit enter. So I get x2 is 1.354, hit it again. x3 is 1.283, one more time. X is equal to 1.266. Oh, x4, so on, so on, so on. And just keep hitting enter. So 5, 6. After 6 iterations, it stays the same. 1.2658709, so on, so on, so on. But we just found another 0 because the 5th iteration is exactly the same as the 6th iteration. So root 2 is 1.2658. Now you could pick other values on that interval. However, they're going to converge to this value here. So now let's go ahead and find another root. So we did the interval from negative 1 to 1. So did that. We did from 1 to 2. That's done. Let's do the other side of this right here. Let's go from negative 2 to negative 1. Let's see if there's something there. Because now, after we've done this, we've searched everywhere from negative 2 to 2. Now, there's nothing special about these intervals. I'm just picking them randomly, okay? Testing them little by little using the results we have from calculus, okay? By using the intermediate value theorem. So, let's see. We found f of negative 1 before. F of negative 1 was negative 7. But now if we find f of negative 2, that equals 109. So we know that there's a 0 somewhere between negative 2 and negative 1. Let's try negative 1.5. So just using my calculator again, I store 1.5 into my x value. I tell it do Newton's method. x2 is equal to 1.354. Oh, I accidentally did 1.5. Negative 1.5 stored into x. So this value is wrong. Here we go. Negative 2.029. x3 is negative 1.845. x4 is negative 1.737. Let's see, 5th iteration, 6th iteration, 7th iteration, 8, 9. After the 9th iteration, it stops changing. So if you compare the 8th and the 9th iteration, they're exactly the same. So we just found the third root, negative 1.6931. So now you could keep repeating this process over and over and over until you find all of the roots. Now, I can tell you that these are the only 3 roots. If you were to graph it, here's a graph. You can see it only crosses the x-axis 3 times. So we found all of the roots. All right, now you would know that it has 3 roots. You would keep testing numbers and see what you get. Like test intervals and see, does the intermediate value theorem apply? If it does not, try a different interval. You're gonna find no other intervals work besides the ones we found. You could apply your pre-calc techniques to see exactly how many roots it should have. There's the Descartes rule of signs you could apply. Like I said, there's the rational root theorem. There's a bunch of other ones that I'm forgetting, but that could help you determine how many you should be searching for. After you know how many you're searching for, that might help you a little bit better. Now, I know I picked like a really extreme example. If I were to ask you something like this on a test, I'm not going to make it to the 7th power where you could think that there's 7 zeros. I might add like 3rd power at most 3 zeros, 4th power at most 4 zeros, something like that. Okay?